This is the complete graph on 5 vertices. You'll notice that every vertex is connected by an edge to every other vertex. We use the notation K5 to denote this graph. Again, the complete graph on 5 vertices is the graph where every vertex is connected by an edge to every other vertex. So now let me draw K4. K4 is the complete graph on 4 vertices. So let me draw 4 vertices. 1, 2, 3, 4. V1, V2, V3, V4. And K4 is the graph where every vertex is connected by an edge to every other vertex. So we need all possible edges here. So here we have K4. Now let me draw K6. K6 has 6 vertices, so 1, 2, 3, 4, 5, 6. V1, V2, V4, V5, V6, and we need all possible edges. There's K6. Now what I want to do is derive a formula for the number of edges in Kn, where n is any positive integer. To do this, what we need to do first is make one observation. And that is that about the degree of any vertex in a complete graph. So notice here the degree of V1 is 1, 2, 3, 4. And notice this is true for any other vertex in the graph. And this should make sense because K5 is the graph where every vertex is connected by an edge to every other vertex. If there's 5 vertices, there's 4 other vertices to be connected to. And so this is true not just for V1, but it's true for V1, V2, V3, V4, and V5. So I'm going to write the degree of Vi here, and meaning for I between 1 and 5 inclusive, and just the whole numbers, right? So V1, V2, V3, V4, V5. Notice also that 4 is 5 minus 1. And so that 5 goes along with that 5 there. Now looking at K4, notice that the degree of Vi is equal to 3 for any I between 1 and 4 inclusive. Right, let's see. V1 is connected to 3 others by an edge. V2 is connected to 3 others by an edge, and so on. So the degree of Vi in K4 is 4 minus 1, otherwise known as 3. And again, you can see this here. And the same thing happens in K6. The degree of Vi is 6 minus 1. And let's just check that for V4 here. 1, 2, 3, 4, 5, otherwise known as 6 minus 1. And so you can see that those go together there. So how about in general? How about for general, for a general n, where n is a positive integer? In Kn, the degree of Vi is going to be n minus 1. And this is true for the same reasons that we saw in K6, in K5, in K4. Right? This goes along with this. We don't allow self-loops, right? So we don't allow this sort of thing. We don't allow that. simple graphs. But there's, if in case 6, V3 has 5 others to be connected to, and we have all possible edges. So in Kn, any vertex, so over here again, in Kn, every vertex has n minus 1 others to be connected to by an edge. So now let's get to the formula. Now remember the handshake theorem. For a general graph G, where a general graph that has vertices labeled V1, V2, Vn, the number of edges in G, this is for any graph. The number of edges in G when the vertices are labeled V1 to Vn, the number of edges is 1/2 the sum from I equals 1 to n, the degree of Vi. Now, we're only dealing with Kn here. We're not dealing with any graph. We're dealing with very specific graphs. So instead of G there, let's put Kn. And in fact, our vertices, as you've seen in this example, are all labeled V1 to Vn. Now, as we've seen already, right, the degree of Vi in Kn, right, is n minus 1. And so if we were to write this out, write out this sum from 1 to n, right, we would have something like n minus 1 plus n minus 1 plus n minus 1. And now how many of these n minus 1s would we have? Right, we'd have exactly n of them. There would be n of these. Right, that's because we go from 1 to n. And so n minus 1, n times, is n minus 1 times n, or n times n minus 1. And so we see that the number of edges in Kn is 1/2 n times n minus 1, otherwise known as n minus 1 over 2. And so that's our formula. The number of edges in Kn is n times n minus 1 over 2.